Good evening. People have joined. Oh, so still we are waiting for the people. Okay.
Hi everybody, how are you? Are you there?
Yeah. Good evening. How are you?
Can you all hear me?
Yes.
Yeah.
Good evening, good evening. Only 3 people joined. Only three people. I don't know how about others. But we have told everybody today we are starting 3
Yeah. Everybody
I
was
think
told.
p.m., right?
Wait
think
for.
that it,
Yeah. Yeah, tell me, Abdul.
I don't think everyone knows that they need to open the same link again. I think maybe some are waiting for another link to be sent. I'm not sure that everyone knows that
But
the
if
same
they're
link
waiting
of
for link,
Verasam
they can
can be.
ask in the
This is my guess only.
if they are waiting for the same link or something, they can put it in the. I worry if they join 7 p.m. Then I don't know. I hope everybody knows. I thought in at the time when we were discussing all 9 people in the line, so that's why I didn't put it in a WhatsApp separately. So what we can do? Can we continue? Can we start and let them join or how? Because anyhow they are getting recording. Maybe some people have that thought.
Yeah. Then it's already 7 minutes past 6 now, so you can start because the people will come. They will join up. Yeah.
Yeah. So anyhow, I'll just text them. See whether any response or anything. Then meanwhile we will start. I put it in the group.
Okay. But prior to you start, I had some few questions on the last lecture, ma'am. Hello.
Hi guys. Hi Gopal. This is Fadil.
Yeah.
I I think you still have a
Yeah,
problem
please
with the
continue.
mic. It's still making that noise.
Now?
Yeah. I mean, every time you mute, it's fine. Oh, now it's better. Yeah. Now it's good.
Okay, okay.
Yeah, you can ask me. What is the doubt? Can you hear me?
Yeah. See, on page number 10, you have written one constant C. So what is this C indicates for, like where all that Prandtl number, Nusselt numbers are written? That C indicates for what? Mr. Fadil, is it okay now the
Yeah.
mic or still it is
Yeah,
very
it's
noise?
perfect. It's perfect.
Okay, thank you.
Yeah,
No problem.
tell me, Gopal, you said you have a
Yes, ma'am, I had few questions. So can I discuss it now or we can discuss some other time?
Hello?
Yes,
Anyone?
Fadil.
Okay, I think there's a problem with the line on her side.
Oh,
Anyways.
is it for the convection? Is it the
this is the problem.
Yeah, Gopal. I think the C you're asking is a constant.
Is it constant,
Because
but what is the value of this constant? Where it is coming?
yeah, because even there was another equation like if you see page 15, like slide 15,
Yeah.
it gives you that Nusselt's equation, and then it says there were C, M, and N are constants. So I'm guessing like in a question like they would definitely give us the value of the C.
C, M, and N are constant. Yeah.
Yeah. So they'll definitely. I'm assuming that maybe at the time of the examination they might give you the value of C.
Okay. And also on
This
the
is what I
question
thought. Yeah.
number 5, on the question number 5, where that length is question number 1, length is given
One exactly. Yeah.
6 inch, where she
I
has
think
taken
length is supposed to be 6 inch, because when I checked other questions, similar questions, they have not like when the heat transfer through a wall, it's only
it will be
it's
on
only the
thickness.
thickness of the wall.
Yeah. It's not taken double, like so. Here
Exactly,
the
that is
thickness
one
will be
question.
6 inch only.
So that's the case, and also in question 2, right?
Yeah.
So we assume like the heat transfers are equivalent.
2 times. Yeah. Actually, it is the two metal of the same size, na. So
yeah, but it's same size, but it's not the same. It's not the same metal, right? So the heat transfers would definitely differ.
yeah, heat transfer will be the same, but it depends upon their conductivity. Another thing.
You are
Because
talking
the
about which
center
problem?
point-
The two metals have the same size, but the thermal conductivity of metal
Yeah.
equal 2 times?
Yeah.
I told you
that
if you
question.
substitute, you will remove. When you
No, it's not. It's
substituting
not
the
about the
equation.
substitution. It's about like how like initially like they've according to the answer they've equated both the heat transfer equations, right? Assuming that the heat transfer is the same.
Yes.
How do
No,
you assume
see,
it to be the same? Like
that's what that's why that the center point where that temperature is T considered, it will not be in between. It will be at a different location. So it may be
no, that is understood. But since it is two different metals, yeah. It's two different metals. The heat transfer, the value of heat, the rate of heat transfer, which is Q, would differ, right? It depends on the property of the material.
No. If heat transfer from one body is going to the other body, it is the same heat transfer it is going. And it depends upon, like the travel speed and other thing will depend upon the conductivity. Suppose you are putting X amount of heat from body A to body B. So it is only the X only, because you are transferring from A to B. So this is the fundamental of this question.
Right. Because when I tried like looking on the internet, like this, some of the similar questions were saying that it is assumed to be at steady state. So which is why they equate Q is equal, like the heat transfer of metal 1 is equal to the heat transfer of metal 2.
No. If it is the metal, same metal, then it is same.
Yeah, exactly.
Even it is correct in the heat flow basically, or this is considered like that only, because you are considering a ideal condition. There is no heat loss to the surrounding.
So you're saying it's an isolated system where the heat loss is
that's
equal
the
to the
only
heat gain.
explanation for it. It has to be isolated.
Yeah. Going from one body.
So the amount of heat cannot, it passes through the system. It doesn't go to anywhere else.
It's not created or destroyed. Yeah, so basically the rate of heat loss is equal to the rate of heat gain.
Yeah. And also on page 7, if you see 17, if you go to page 17.
Yeah.
See, here is saying laminar flow is equal to Prangle number should be greater or equal to 0.6, okay? And Reynolds number should be greater than 5, x 10 to the power 5. But if you see the turbulent flow, okay, if you are seeing the turbulent flow,
I think the sign is there's a mistake with the sign.
Yes,
it should be the other way.
I agree, because it doesn't make sense. Yes.
First one should be less or equal to.
It should be greater than 0.6 and less than 60.
No. In the laminar flow, it should be less or equal to 0.6.
Yes.
And it should be between 6 and 60.
Yeah. Basically, that's the range between 0.6 to 60.
Yeah.
And same with the Reynolds number as well.
Yeah.
Yeah. So that would have been a mistake.
So less than 6 and equal to 6 will be a laminar flow, and over 6 it should be
over 60
again,
will be
over 6. No. Again, it is something wrong.
No. So in this case, basically, for tubular flow, it is always over 0.6.
It should be always over 0.6 yet.
Yeah.
I think so. And less than 0.6. But why this 60 is coming here?
Yeah.
What does this
Probably maybe there's another flow which is more turbulent than the normal turbulent flow.
Maybe. Okay, and have you seen where she is not joining? What is question 5?
Can you all hear me? Can you all hear me now? Actually,
Yeah.
I am also talking in between, but you all can't hear me. So I have disconnected and connected back.
I think you were on mute the whole time.
Yeah.
I don't know. There was some internet connection problem. Now it is okay, I guess, right? Can you all hear me now, right?
Yes.
Yeah. So all the doubt has been sorted out, or is there anything you no? I need to explain.
No, ma'am. Question number 5. If you go.
Okay.
Question number 1.
5.
Question number
the
first question.
Okay. First question also. See, I think that thickness is 6 inch, and we should consider 6 inch, because you have in the calculation calculated 12 inch, which is I think from where we are getting 12 inch. I don't know.
See, if you are going to the question is talking about heat of conduction per unit area. So if it is per unit area, then you should consider the furnace both sides. That's why there is a 12 inch. One side it is a 6 inch, another side is a 6 inch.
one side 6 inch and the other side 6.
Another side. The
So you-
wall thickness means there is a both side the wall we are talking about. Okay. So the question
ma'am.
is talking about the heat of conduction per unit area. If they are talking about rectangular or something, they're given the height or anything, okay, you can calculate the area also because you know the thickness, you know the height and the breadth. So the question is talking about conduction per unit area means you need to include both side thickness. That's why it is a 6 inch.
Acha, acha.
I mean 12 inch, 6 into 2.
Okay, okay.
Okay, what is the next question?
Question number 5, this ice melting,
Ice melting. Okay.
Yeah, see, it is saying 30% is lost. Now,
Okay.
if you see the 80 calorie per gram ice is melting, so 0.85 into 80, okay,
Okay.
and it is 70% only effective because 30% is lost.
Yeah.
So it should
Yes.
be multiplied by 0.7, is it not? Whereas in the solution, you are dividing it by 0.7.
No, because we're dividing 0.7 to find out the total energy.
Exactly. So we need to
Huh?
calculate the total heat transfer, right? So for that you need to divide it by 0.7.
Why? See, I want to know the total.
Because only 70% was used to melt the ice, and the remaining 30% was used to.
Because simple.
Remaining 30%.
The surrounding.
If you multiply by 0.7, then the efficiency of the system increases. It has to be a loss. So you have to divide it by 0.7. Otherwise, you are basically making the system efficiency increases.
No,
The
no.
opposite.
See, how much heat is going to melt the ice? How much heat?
It's only the
Transfer
70% of the. Okay, please listen. Okay, so there is a metal rod. Okay, let me share the screen. There is a metal rod, a hot metal rod, which is put it in ice water, right? So there is a total heat conducted. In that 70% only used to melt the heat. That
Okay.
means I would say 0.7 Q by T, which is equal to you have to have a MLF by T. Understand? The formula here, if you see Q by T equal to MLF by T, right? M is the mass, latent fluid heat of ice divided by the time, right? So that means that is equal to 0.7% only. 0.7% of QT only it's used to melt the heat, melt the ice. So that is why the 0.7 is divided by here. It's not, if you multiply, then in that 30% is gone. Then you only get 40% of the total heat only used to melt the ice. Understand?
Oh, okay, that.
Yeah. Okay, any more doubt?
One more.
Good. I mean, better you all have gone through the slides. That really,
Question number
makes me
6.
more,
Question number
any
6.
more doubt?
It says transition from laminar to turbulent zone in free convection heat transfer is governed by the critical value of. Now there are 4 options, but we chose option D, as in option D is the answer, right? But
Yep.
So transition from laminar to turbulent doesn't involve this Grashof number, is it?
How you are saying? Grashof number not involved?
Isn't it related to the slide number 17?
Slide number 17. What is that in 17? Slide number is
16.
talking
Sorry,
about the
slide number 16 and 17. Because here, I mean, like all the equations have either the Reynolds number or the Prandtl number.
Look, the answer is correct for a simple reason. I checked the internet and the answer is like this. So he didn't write it wrong. If you check the internet, the same question, you will find the same answer.
No, I'm not saying it's wrong, but like where exactly is the answer to this question? Like, is it on the slides? Like, does it say that like the transition from laminar to turbulent has any of these parameters?
1 minute. Let me check again.
The slide 17. Slide 17 talks about forced convection.
Yes,
free convection.
that's what I was trying to. This is for the forced convection. From slide 14, you can see it's for forced convection, right?
Okay, I
For
understand,
forced
but then,
convection, you have to take into consideration of Reynolds number.
but where
That
in this
one is clearly says it's a free convection. Then it is
slide?
this formula.
Which formula?
You can go to slide number 10. Nussel number equal to Kirchhoff number, Prandtl number. That's a formula.
Oh, okay, okay, all right, okay.
Slide number 10.
This is, you mean to say this is natural convection?
So for forced convection, you have a Reynolds number. Forced convection, you have a Reynolds number and Prandtl number. But free convection, you have only Kirchhoff number and Prandtl number.
Sorry, you said pre-convection?
Right?
Free convection.
Free
Okay,
convection.
okay, okay. Right,
Yeah.
okay, okay.
That means it's a natural convection.
Right, okay.
Right?
Yeah. Okay, then let's
Any
move
more doubt?
on.
Any more doubt?
I think that should
No?
be
Nothing?
from my end, it's fine.
Right? Okay. Then let's move to today's topic. So everybody has joined. So far, 3, 4, 5, 6, 7 people joined. So it's okay. Let's start. So today I plan to start thermodynamics. Since we saw last class heat transfer, just continue with the thermodynamics, right? Some basic theoretical chapter of thermodynamics. Then we can go with the more questions. Here thermodynamics, more theoretical questions. There is some problematic questions also, but there are more into theoretical questions. Sometimes it is 1 or 2 problematic questions also there. Let's see that one later. Let's start with the thermodynamics chapter. I hope you can all see my screen. Otherwise, you can open thermodynamics chapter in your laptop. So here I face some internet connection disturbance. Now it seems to be okay. Let's see. So now the first slide, we are talking about the different system, right? There is energy, the open system, closed system, isolated system. Yeah. Can you all hear me?
So you were
Anybody,
talking process calculation or thermodynamics?
Thermodynamics.
Thermodynamics is a different slide you are showing. It's a process calculation you are showing here on the screen.
Process calculation, but energy balance. It's energy balance.
Okay.
It's an energy balance in the process. Like, we are going to see about the work, heat input, heat released, then what is the work done. So that's also a start of process calculation, but not mass balance. It's energy balance.
Okay.
I can say it's a thermodynamics actually. The topic in the slide I have saved as a thermodynamics, but
Okay.
if you say into technical term, we can say process calculation, material balance is our mass balance separate. That will only talk about what is the quantity, what is the percentage, right? That is all mass balance or material balance. This is the energy balance. Okay. So now we are at the slide which I show you, open, closed, and isolated system. Open system means in which you can add or remove mass, right? That's open system. You can add and also you can remove mass and also heat. That is what called open system. But closed system means you cannot add mass, right? But you still can add or remove your heat. If there is a heat, you can add or remove. That's called closed system. Isolated means neither mass nor heat can be added or removed. That's called isolated system. So that's what we have seen here. If there is a mass, add or remove. So there is a maybe heat or add or remove. Accordingly, the work will be done by the system or sometime on the system. So if it is a boundary, the boundary is very rigid, means mechanical work cannot be done. Right? If the isolated means no interaction are possible. Right? That is what we have given here. Let's move on to simple system, isolated system, no exchange of matter or heat. Closed system, there is exchange of mass or heat. Because Gopal, you have some mic problem, it is giving some disturbance. Papa. Right. So now, if anybody has any doubt, you can unmute and you can ask me. Okay, because I mute all the person. If any has a doubt, you can unmute and you can ask me, no problem. So now, before doing energy balance, you should know what are the different type of energies involved in a one system. So there are three type of energy. One is kinetic energy, potential energy, internal energy. Kinetic energy, energy due to motion of a body. That's a formula. You can see half m v square. M is the mass, v is your velocity. That's a kinetic energy. The next one is the potential energy. Energy due to the position of body in a potential field, maybe gravitational or electromagnetic field relative to the given reference. That is a potential energy. The formula is mgh. M is the mass, g is a gravitational constant, h is the distance or the height. Right? That's a mgh. Next is the internal energy. That's called delta h. Delta h is the change in the phase, like vapor phase internal energy minus your liquid phase. That's the internal energy. Internal energy cannot be measured directly. We can calculate from other variables. Internal energy of a system depends almost entirely the chemical composition and the state of the particular system or molecules inside the system and the temperature of a system. So this is all internal energy. So when you transfer the energy, so when you're talking about heat, work done, there is a energy transfer as a result of temperature difference between the system and its surrounding, right? That is a energy will be transferred. If a system and its surrounding are at same temperature, then Q equal to 0. That means the system is a adiabatic. There is no heat transfer between the system and surrounding. That means Q equal to 0. That means temperature is going to be same. Then it is adiabatic. So work means W. That's a work energy transfer via a mechanical moving mechanical part, could be impeller or turbine, or moving the system boundary against the pressure, right? That is also can be called as. If it is against the pressure, it is a delta PV. So generally, according to the law of energy conservation, total energy is nothing but delta U. That's energy, internal energy difference, kinetic energy difference, and the potential energy, which is equal to Q plus W. Q is the heat transferred, and work is the W. Work is done. The work is, if it is done by the pump, then it is a negative. Work done on a system, it is a positive. If work done by a system, W is a negative. That means the same formula, if it is work done by a system, Q minus W. If it is work done on a system, then it is a positive. The same way for Q also. If Q is removed, then it is minus. When Q is added to the system, then it is positive. That's right. When heat transferred from a system, that means the heat is removed from the system, then it is negative. When the heat is added to a system, then it is a positive. So here potential energy, we saw mgh. Gravitational constant is 9.81 ms to the power of minus 2. Kinetic energy is half m v square. So internal energy, delta H is nothing but Hi minus HL, which is nothing but mCp delta T. M is the mass, Cp is your specific heat at constant pressure, delta T is the temperature. So specific enthalpy change, Ui plus PVI. That's the enthalpy change we can talk about here. Now they are talking about the specific heat at constant pressure and constant volume. This means it's amount of heat required to increase the temperature by 1 degree Celsius. So when the heat is given at constant volume, right? That's a CP. Specific heat means in order to increase 1 degree Celsius, how much heat is required. At constant volume means it's a CV. Constant pressure means it's a CP. Normally compared to CV, CP is a very commonly used. CP generally it will be higher than the CV. This is what here. Why it is specific heat constant pressure greater than a constant volume, right? Because when heat is added, pressure, right? The substance expands and work. That's why the pressure get increased. So CD delta T, if you say MCP delta T, if you see CV delta T, because if it is no work done, That is nothing but a QV equal to CV. So generally, because of the work done or work not done, because of that reason, the CP will be greater than CV always for any gas. Specific heat of air, CP and CV, there is a ratio. For air, it is, I think, 1 point something. Remember this nominal value of used for air at CP is 1 kilojoule per kg and CV is 0.78. So the ratio K is nothing but 1 by 0.7, I guess. Yeah. So which is 1.4. That's a ratio of specific heat between pressure and volume. We saw already why there is a two value of specific heat. One is at constant volume and one is at constant pressure. For water, for ice and water vapor, there are different specific heat. I didn't hear that there may be a question about the specific heat of ice or water or anything, but there is one time I heard there is a ratio of a specific heat of air. K equal to 1.7 or something they have asked. Joule's law, enthalpy, that's a PV equal to RT. So that's what when we're talking about R is a constant, that's a gas constant we talk about. PV equal to RT. And when we're talking about enthalpy of ideal gas, we will talk about PV equal to nRT. That we will come later. So when talking about different type of system, we saw open system, closed system, isolated. Now there are two more systems, which is homogeneous and heterogeneous. Homogeneous means the two different phases consist, it will be well mixed, then it will be a single phase. That's a homogeneous. Heterogeneous means there will be still two separate phases. That's a heterogeneous. Boyle's law, right? When talking about the Boyle's law, it is a P directly proportional to V, isn't it? That's a Boyle's law. P indirectly proportional to V, right? That's a Boyle's law. There are three laws which combines together, it forms the ideal gas law or gas law, PV equal to nRT. P indirectly proportional to V, and Charles law talking about V directly proportional to T. That's a Charles law. But all are here whenever talking about temperature, it should be in a Kelvin. And we talk about Charles law, Boyle's law, and one more. Gas loser gas law. This is talking about P indirectly proportional, V directly proportional, P directly proportional to T, right? Pressure directly proportional to T, and volume directly proportional to T, that means temperature, and pressure indirectly proportional to volume. So combine this, you will get a three laws. Combine this, you have a. So when you're talking about as per Charles law, you have a V1 by T1 equal to V2 by T2, because V directly proportional to T. So that means V1 by V2 equal to T1 by T2. P directly proportional to T, that means P1 by T1 equal to P2 by T2. That means P1 by P2 is nothing but T1 by T2. That's gas loser. Only Boyle's law will be in a reverse. At constant temperature, P indirectly proportional to V. That means P1 V1 equal to P2 V2. That means P1 by P2 is nothing but V2 by V1. So Charles law talking about at constant pressure, gas loser at constant volume, Boyle's law at a constant temperature. So put together, you will get a PV equal to nRT, right? N is the number of moles, molecular weight we can talk about. PV equal to nRT. R is the gas constant. When you're talking about molecules, gas, ideal gas, so we should think about the Avogadro number, right? 6.0221 into 10 power 23 per mole. So what is Avogadro theory? They're talking about all ideal gas at a given volume will have a same number of molecules. That's a Avogadro theory. A given volume of V, any ideal gas will have the same number of molecules. The mass of the gas will then proportional to the molecular mass. So he is talking about in terms of Avogadro number. which is Na. Avogadro number is 6.0221 into 10 power 23. So using that also you can calculate your kinetic energy, which is 2 by 3 kT. K is your Boltzmann constant. R is your gas constant, which is 8.3145 joule per mole Kelvin. Whereas K 1.38 into 10 to the power of minus 23 joule per Kelvin. All these constant you have to remember. Even gas constant, there is a two of gas constant. One is in a joule 8.314. I think we will have another unit R value also there. In liter mole, in that we have another value. Two value there in gas constant. Please remember that before going for exam. Okay, now we are going to see about the this one, Dalton's law. So in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of partial pressure. Sum of partial pressure of individual gases is equal to the total gas pressure of that gas mixture. That is a Dalton law he's talking about. So what? PV equal to nRT. N is the number of moles. This is what I said. There is a 0.081 liter atmosphere per mole per Kelvin. This is one value. Another one is 8.3145 joule per mole Kelvin. That's another value. Always atmospheric pressure 760 mmHg. Temperature should be in Kelvin. So you add whatever in degree centigrade, you add 273 in order to get a Kelvin, and volume should be in a liter. Generally, mass is the one. If it is ideal gas or non-ideal gas, PV equal to MRT only. So when you substitute at constant volume, means is a volume. Yep.
What's an ideal gas and what's a non-ideal gas? What is an ideal gas?
Means it behaves in the same way. Number of, this is very, very basic chemistry if you ask me. Non-ideal gas will not have the same number of molecules, right? Number of molecules will not be the same. If you take it in one volume, the ideal gas will have the same number of molecules, whereas a non-ideal gas will not have that. And the movement of non-ideal gas also will be different.
Okay, just clarifying. Thank you.
Right. So that is a difference between the PV equal to nRT only applicable to the ideal gas. Non-ideal gas will not have a PV equal to nRT. Actually, it's a PV equal to MRT. That's why, because there is a mass should be involved in non-ideal gas. Because number of molecules will not be which occupy the same volume we talk about, right? That's what it is here. We can see we can use the ideal gas law, which is in terms of mass equations here. See, thermodynamics is a big chapters. You know, we will have a thermodynamics 2 or 3, I think, in our 4-year subject. We can't cover complete things here. At least we can touch the key thing, right? The bullet points, which can cover the questions or overall. That's what we can say, right? Because thermodynamics is a big and vast topic. I don't know who are all very good in thermodynamics, but I'm not really good in thermodynamics. A gas at standard temperature and pressure has a, this is, you know, what is a standard volume? If you know the standard temperature, if you know the standard pressure, we can calculate. What is the standard volume? Anybody know before you're calculating anything? Standard volume.
22.4 liter, I think.
22.4
liter, I think.
Okay, so we can use the same PV equal to nRT. So if we calculate V, same way, 22.4 liter, right? So that standard volume is being calculated from this formula only, where you have used R equal to 0.0821. So standard temperature is 273. Pressure, standard pressure is 1 atmosphere. So now we are going to talk about the Carnot cycle. We know we all talk about the work done, heat transfer to the system or from the system, right? That's all form a heat engines. This is a Carnot cycle. That net work done by the substance during the cyclic process, right? So when you're talking about here, the temperature from A to B, if you see the pressure is increasing and temperature also increasing from A to B, different temperature. You can see the next slide here. If you see here, So if you see 4:1, so this is the adiabatic process, right? So the temperature is changing, adiabatic process, and pressure is temperature is 300, pressure is increased 5. The volume here, so from here to here the temperature increase, and then from here it is a isothermal process. From 1 to 2 is a isothermal process. Temperature remains constant, pressure decrease, then volume increase. So 4:1 is a constant volume. Very minor change when you see here, but it's a something like constant volume. The pressure increase, temperature increase. 1 to 2, temperature is remains same, and the pressure also decrease. So you can see the pressure decreased. That's why from 5 to 4 it is done. Then you have a volume also increased, right? That's called isothermal. Then you have again 2 to 3 adiabatic. Then again you have a isothermal. This is a 3 to 4 is a isothermal. So when there is a one temperature, when you start to reduce by internally thermodynamically, there is a 4 process, 2 adiabatic, 2 isothermal process is happening. That's a called Carnot cycle we talk about here. So the work done by the system, which is represented by 1, 2, 4, 1, 2, 3, 4. That's what in the previous slide they talk about. The area which is talking about A, B, C, D, right? That or CDA. So when you see here in isothermal, heat is added. When in 1 to 3 to 4, the heat is removed. Here from here the temperature same. So that's why heat is removed here. So that's why Q1 minus Q2, right? You can see the Q1 is added to the system, whereas here Q2 is removed from the system. So in both isothermal process only the heat is added or heat is removed. That's why the total work done is nothing but Q1 minus Q2. This is called Carnot cycle. So when you're talking about the Carnot cycle, the percentage of efficiency, we can talk about this formula T1 minus T2 divided by T1. T1 is your higher temperature, so T2 is your 200 here, right? That's a T1 minus T2. Work done is nothing but Q1 minus Q2. So percentage of efficiency, you can calculate W by Q1. W is the work done divided by the heat added to the system. That's a Q1. Entropy change, which is nothing but Q2 divided by T2. So always remember T must be in Kelvin. T1 and Q1 is a temperature or heat added to the system, and T2, Q2 is a temperature, heat released or rejected or removed from the system. So now there are some more process just to recall. Throttling process. Throttling process means you have in a narrow or constriction. So you high pressure fluid you pass through. That's a throttling process. Throttling process involves the passage of a high pressure fluid through a narrow constriction. The effect is a reduction in pressure and increase in volume, right? So when you put it in volume will be increased and pressure will be reduced. This process is adiabatic. So no heat flows from or to the system. It is not a reversible, right? And it is not an isentropic also. The entropy of a fluid actually increases during this throttling process. So such a process occurs in a flow through porous plug, or you have a orifice, right? That kind of a process, you will have a Joule-Thomson effect. Throttling process is a thermodynamic process in which enthalpy of a gases remains constant. Enthalpy constant and entropy is not constant. Isenthalpic process, no work done by the system and no heat transferred from or to the system, right? It cannot be isentropic. It is a fundamentally irreversible process. Right? No work transfer, no heat transfer, irreversible, isenthalpic, not isentropic.
I think this process happens in the cooling cycle, right?
Cooling, or where you want to decrease the pressure or control the pressure in such a way, needle valve or orifice, or some kind of porous plug, they put it in the pipeline such that the volume will be increased and the pressure also will go for a P in, actually always greater than the P out. So high pressure you can reduce it to low pressure. Two way, either you increase the size of the pipe, that also will reduce the pressure. Or you can introduce this kind of throttling valves which controls the pressure also. Why it is cooling? Because here it is no work done, no enthalpy. I don't think it is for cooling they have to use. I think they, in order to reduce
this
the
is
pressure.
one step during a cooling cycle. After you, let's say the freon you have, the freon, let's say he gets hot, and then after that you pressure it and then you throttle it, because when it gets the throttling process, it decreases its temperature, so he becomes cool, so I can use it to cool another substance. That is it's one step during the cooling process.
Maybe because volume increase, right?
Yes, volume increase and temperature decreases.
Temperature decrease, maybe because of that. Volume increase, yeah. This is what we saw here in volume increase. If you see here, volume increase, the temperature should be remain constant, right? This is what isothermal process. They're talking about throttling process is adiabatic, isn't it? I read somewhere it is an isentropic increase. During the throttling process, no work done. See, there is no heat transfer. That's what I said. There is no heat transfer here. It cannot be the temperature decrease is possible. It's adiabatic only. That means volume change only happen. No temperature, no heat transferred or no heat added to the system in the any throttling process. Enthalpy of a constant gas will be remains constant always.
Yes,
If it is enthalpy is same, if enthalpy is same, then there is no heat transfer will be done, right?
Yes, no heat transfer, but the temperature decreases. That's for sure.
If temperature decrease means there should be heat released. Otherwise, how the temperature will be reduced?
Then it is also isothermal process. It's adiabatic process. It is not an isothermal process. If
it's
the process cannot be both adiabatic and isothermal, it has to be one of them.
That I agree. That cannot be. Yeah, one process cannot be isothermal. One cannot be same process cannot be adiabatic. It's adiabatic. There may be a temperature. When you see this one here, 4 to 1. Yeah, there may be some. If you see 4 to 1, is a temperature change is possible from here to here. The 4 to 1 is adiabatic. Yeah.
For sure, so the temperature decreases increase, because you measure the
volume increase. Then yes. Volume here, if you see volume is slightly decreased. 4 to 1 here. The pressure is decreased. In throttling process from 1 to 4. So if 1 yes. to 4 pressure decrease, then temperature decrease.
Yes.
Yep. So this is what 1 to 4 is adiabatic. In throttling, it's not 4 to 1 because from high pressure to low pressure it is coming. So then the pressure is reducing, right? So that means the temperature also decrease by seeing this curve, adiabatic curve, correct? Right. So that's what talking about the no work transfer, no heat transfer. It's not irreversible. It is isenthalpic. Free expansion, also called free expansion, it's an irreversible process. Volume of gas kept in one side. This is called free expansion. Right. Isolate the container. The same thing, but instead of the orifice, we put it in a vacuum stage, right? The piston or something, we put it in a vacuum, or because of the pressure, it's automatically released. There is no heat transfer and work transfer from to the system. So as a result, here, free expansion, it is going to be temperature before and after expansion is going to be same. This is a isothermal process, right? In throttling process is not a isothermal process, whereas a free expansion will be a isothermal process. Right? This is a free expansion. If you see pressure, temperature, volume in decrease, the pressure also decreased. Volume is increased. From here, volume.
Excuse me, ma'am. Can you explain what free expansion is again?
This is a very good example of free expansion. There is no forcibly throttling or orifice or something. We didn't do it.
So there
But
is
it
no
is
work
not.
done on the system.
Yes, that's why you can see in this process, no heat transfer, no work transfer. So because of that, the temperature remains constant here. There is no work done, but it's automatically free expansion. It is happening. So that means pressure reduced, volume increase, temperature is constant.
Mm-hmm. Okay.
It is natural expansion.
Yeah, that's why
All
it's
right.
called a free expansion. So here, if you see volume is increased, V2 equal to 2, V1, then pressure is reduced, P2 equal to P1 by 2. So no work done, delta U equal to 0, W also 0, Q also 0. Now the next important factor which is talking about thermodynamics is LMTD, logarithmic mean temperature difference, which is used to determine the temperature. Right? When you're talking about the cooling system or heat exchanger, they used to talk about this LMTD. What is this LMTD? If you see this diagram, you will understand. So this is a parallel flow heat exchanger. This is a counter flow. If you see parallel flow means the cold fluid and hot fluid in a parallel direction. So they are in cold fluid, in hot fluid in the same direction it is going. And the LMTD formula is delta T1, which is delta T1 is the difference between the THN minus TCN, right? The cold fluid and hot fluid input temperature, that's a delta T1. And here it is a delta T2 out. So LMTD formula is same, delta T1 minus delta T2 divided by Ln delta T1 by delta T2, but depends upon the parallel flow or counter flow, the delta T1 formula will change. If you see here in counter flow heat exchanger, hot in minus cold out, that's because it's in opposite direction, so you have a H in and C out. So delta T2 is this. So LMTD is a logarithmic mean temperature difference. That why we have to calculate this, that will determine your heat transfer efficiency or how it is being done. That will help in order to calculate your heat transfer rate in the heat exchanger system. So that's why use of LMTD will help in the analysis of heat exchanger with the constant flow rate and some with the thermal properties. So if a constant area and heat transfer coefficient is also constant, higher the LMTD, more heat is transferred. So the same thing it is explained in if it is a co-current, that means here you have a delta T1, this is a delta T2. And if it is a counter current, this is a delta T1 and this is a delta T2, right? So from now onwards, we are going to see only the question. Because we have a mechanical engineering also, they have a thermodynamics. So I combine the mechanical engineering questions also. Okay, let's see the first question. Answer is there. Water is pumped from storage tank through a tube of 3 centimeter inside diameter at the rate of 0.001 meter cube per second. Kinetic energy, that means half mv squared, right? EK, the formula is half mv squared, isn't it? We saw in the first slide. Here. And this is the half mv squared. V is your velocity, which is in a meter per second. But what is given? It's in a meter cube per second. The flow rate is given in the question. So how to calculate the flow rate?
Divide by area.
Velocity from flow rate?
Divide by area.
Divide by area, very good. Okay, so now can you calculate divided by area and tell me? Yes. Yeah. So they're talking what is the kinetic energy per kg. That means they're asking EK by M. That means it's nothing but half V squared only. So if you calculate V, then it is okay. So then water is pumped through a storage tank through a tube of 3 centimeter inside diameter. So The area here, pi r squared.
It's pi r square.
Yeah, can you calculate and tell me whether is it correct? Centimeter convert into meter. Then you get the area, volume divided by area. That gives your velocity. And see, are you getting 1 joule?
Yeah, 1 joule.
1 joule. So here. So this is pi r squared. That's what they put, pi d squared by 4. So convert into meter. So which is nothing but 7.068 10 power minus 4 Q by A. Then it is 1.41 meter per second. So 1.415 meter squared per second squared. That means 1 meter squared per second squared is nothing but 1 joule. That's a unit conversion. 1 meter squared per second squared is nothing but 1 joule. So it is 1 joule per kg. Next, they're talking about the root mean square velocity, RMS, right? So which is a root 3 RT by M. Gas constant, when you're talking about here, 8.315 joule per kg mole. Takes into account both molecular weight and temperature that directly affect your kinetic energy. So the kinetic energy, so far we saw just the EK, which is only talking about the velocity only. But when you're talking about root mean square velocity for gases, that means you should take into consideration temperature also. In the previous question, there was no anything talk about the temperature. If there is the gas or the water or something, it is heated at some temperature, then you have to take into RMS first. So root mean square means root of 3 RT by M. So M is your molecular weight for oxygen. Here the question is about oxygen. So oxygen molecular weight is 32 kg per mole, and R constant is 8.315. Temperature is given at 298 Kelvin. You can take that one. So here velocity is 482 meter per second. Then this value you put it in EK equations. Right? Then you will get a kinetic energy. Next question. Water is pumped from a storage tank 1 to tank 2, which is 40 feet above tank 1. Potential energy. Potential energy increase with each kg of water from tank 1 to, that means mgh, right? H is 40 feet. Gravitational constant is 9.8. Only thing, feet you need to convert into meter. The question is EP divided by M. Can you just calculate, convert feet into meter, then tell me what is answer? Is it correct? (9.81 meter per second squared). 40 meter. If you 40 feet convert, you divide by 3.28. Right? 1 feet equal to 3.28. 1 meter is 3.28 feet. If I'm not right, correct? Are you all hearing me, or I keep very silent? I'm saying. All can hear me?
Yes,
Yes, yes, we are muted, so we are hearing you, no problem.
Yeah, no problem. Okay. So 3.28 feet equal to 1 meter, right?
Yeah.
Next, what is the enthalpy change of 150 gram of formic acid from 40 degree to 85 degrees centigrade at what atmosphere? Cp is given. So then mCp delta T. M is given, Cp is given. Can you calculate and tell me? mCp delta T. What is the answer for question number 3?
Is it A?
A.
mCp delta T, because you can straight away you keep it as a degree centigrade because it's going to be difference only. So answer is A. Okay, now there is a 2 stream they're talking about. One stream is 120 kg per minute. That means mass flow rate that is given and 30 degrees centigrade. and enthalpy is given as H is given kilojoule per kg. Then another stream with a different temperature. So two streams are getting mixed. How much heat should be transferred if the system has an output? The output is 295 kg per minute, saturated steam. H is given. How to calculate? How to calculate? They have given two stream mass flow rate and temperature. Each stream temperature is given. H is given. Then they are talking about output stream mass also given.
I think we
temperature
should
also
substitute
given.
in the equation H1 M1 plus H2 M2 equal H3 M3, right?
Okay. Okay. H1 M1. That means here straight away multiply. See here the kilojoule per minute. So if you just multiply by 125, because if you multiply kg will be cancelled, kg per minute, kilojoule per minute. So here also kilojoule per minute, right? So then you can minus it off. H out minus H in. So in the H in you have a two stream. That is the one the heat will be transferred. Am I right? Can you calculate and tell me?
Okay.
H out minus H in. H in you have a two stream. What is the total H? Total H in, and then H out also you can calculate multiplying by here. Then you will know the difference. That will be the heat transfer to the output, kilojoule per minute, because the total heat transfer from input to output only. What is the answer? Anybody calculated or not? What is the answer? Can you all hear me? So 125.7 multiplied by 120 plus 272 multiplied by 175, right? So that you have to multiply 295 multiplied by 273 minus the total of this. Everybody getting C? Anybody have tried?
Yes, see.
C? Sure?
Yeah.
This one, here, that is Q equal to delta H, that's the enthalpy. So delta H out minus H in. So then you have to multiply this 295 multiplied by 2793 and you add all the H in. So whenever they're talking about the chemical, kinetic energy and potential energy, you can ignore it because involving the phase change. Whenever there is a phase change, chemical reaction or large temperature change, then the total heat when you calculate, you can ignore your kinetic energy and potential energy. Here 8 megapascal and 400 degree, specific heat internal energy is given, specific volume is given, specific enthalpy. How to calculate this? H equal to U plus PV, where we see, we saw in the slide, if we see H equal to U plus PV, the internal energy or enthalpy. This is here. Not here. So if you see H, internal energy, kinetic energy, here. Here, the specific enthalpy change is nothing but U plus PV. So the volume is given, internal energy is given, the pressure is given. They're asking the enthalpy, HI. So U is given is the internal energy 2864 and pressure is 8 megapascal. That you need to convert into Pascal or kg per kg per minute, if I'm not wrong. They convert it into kg. That's what 8 into 10 power 3. The volume, it's a 0.0324 meter cube per kg. So then total you will get a 3138 kilojoule per kg. This is all previously asked the question, and the question number 6 also. See here the figure shows an enthalpy concentration chart for water. The heat evolved when 50 lb of water is mixed with 100 lb of sulfuric acid at 77 degree Fahrenheit. With the final solution temperature is 77. So final solution temperature is 77, 50 lb of water and 100 lb of sulfuric acid. What is the graph is talking about is a mass fraction of sulfuric acid on the heat evolved the solution. This is a mass fraction of sulfuric acid, right? The mass fraction is 0 means, that means it's a pure water. Mass fraction is 1 means it's a 100% sulfuric acid, right? So they're talking about temperature 77 degree. So what is the heat evolved 77 degree Fahrenheit? This is a 77 degree Fahrenheit. If you see here, right? 77 degree Fahrenheit. You have to take into mole fraction. How to calculate mole fraction? Because you can see 50 lb and 100 lb. That means total become 150 lb. 50 by 150, that gives your 0.66. So it's a mole fraction. Mass fraction is a 0.66. So then you take a concentration is a mass fraction 0.66, 77 feet. That is a 77 degree Fahrenheit. You take a, this is a pure water. The BTU is it a 45 something, and here for the pure sulfuric acid is a -5 BTU they are taken. So when you see here the calculation, same way, enthalpy of mixture minus 100% water plus 100% sulfuric acid. So then enthalpy of mixture, that is nothing but you can take it from here, because 77 degree Fahrenheit 0.66, that's a mixture. So here that enthalpy is minus 125. So when you substitute here, minus 125 into 150 minus of 45 into 50 minus 100 into 5, then total is a 20,500. So something around here, D is the right answer. So you are clear? This is very, very often repeatable question. They have given a chart of mass fraction versus the heat evolved for a mixture. So then the key thing is you need to calculate the correct mass fraction and then get the pure water heat enthalpy and sulfur 100% sulfuric acid enthalpy, then the mixture enthalpy, then same way H out enthalpy of mixture minus enthalpy of a sulfuric acid plus a pure water. That gives your answer. Clear? Any doubt in this question? No?
Ma'am, can you please once again
Can you proceed to the next
problem?
Yeah. That's what. What is your doubt here? I couldn't hear you.
So just explain it once more.
Okay, right. See, the question is talking about you need to calculate the heat evolved when there is a 50 lb of water and 100 lb of sulfuric acid is mixed in, right? And the final solution temperature also they put it as a 77 degree Fahrenheit. How to calculate the heat evolved? That means the enthalpy of that particular enthalpy released. That's what if you see in this equation they talk about here, the heat removed or absorbed, that is nothing but enthalpy of the mixture minus enthalpy of a pure sulfuric acid and water, right? So how to calculate, how to know the enthalpy of a mixture, how much, and sulfuric acid how much, and water how much? For that you have to use this particular graph. Okay, here 50 lb of water mixed with 100 lb of mixture, that means total become 150 lb. So that means the mass fraction of water is a 50 by 50 by, 100 by 150, because we are talking about the sulfuric acid mass fraction. So 100 by 150, which is nothing but 0.66 mass fraction. So that is the mixture, right? So it's a 0.66 mass fraction of sulfuric acid. So you take 77 degree Fahrenheit curve. So this is in the third one. That's what they have. Now I can make it in a zoom I'm giving. So this is 77 degree Fahrenheit curve, right? So here, if you see mass fraction from 0 to 1, right? That's a mass fraction of sulfuric acid, which is talking about 0 to 1. So if it is a 0, means it's a pure water, right? You can see the curve 77 degree Fahrenheit curve, which is heat at the 0 mass fraction of sulfuric acid, that gives the water enthalpy. Then the same way, if it is a 1, means it's a pure sulfuric acid enthalpy. Then at 0.66, the mass fraction sulfuric acid, that's a mixer enthalpy. So then the difference is the heat removed or absorbed. So if you, what you have to do? Enthalpy into the mass, 150. The total weight of a mixture is now 150 minus enthalpy of water into 50 lb, enthalpy of sulfuric acid into 100 lb. These are the mass. Then when you find out, it is a 20,500. Since it's a negative, that means heat is released. That's why it is a negative, 20,500. So here, the closer answer here, it is a 21,000. Why there is a some different? If you see, exactly we can't get here. It could be -5 or we do not know exactly. And here also exactly we couldn't get. So something more or less we can say it's a 20,000 plus. So that's why the answer here chosen as a D, 21,500. Clear now? Any more? Anybody? Anyhow? Any doubt?
Madam, this 21,500 is sure, no? Because somewhere I received the answer 18,750. Calculation is correct or wrong? I don't.
So then can you check here? Can you check this calculation? Because 18,750 only the enthalpy of a mixture only, right? If we see here. But the question is how much heat, they're not asking about the mixture, right? They're talking about heat evolved. That means heat released. They're not asking about the enthalpy of a mixture. 18,750 is only the enthalpy of a mixture only. I mean enthalpy into the mass of a mixture only. But it is not showing about how much heat is evolved.
Okay, okay.
Right? So this is what I would say. So 18,750 cannot be. The mixture itself 18,750 means cannot be the same heat will be released. It should be a little bit higher than that, right? Then only the heat of mixture is going to be 18,750. I guess. So I would say 20,000 should be higher than 18,750. Any value, if it is above 18,750, if there is a 2 value, then I would say maybe, yeah, whichever near to 20,000 I can choose.
Oh.
So they have given the explanation also. They have taken the same question from some book. So that's what you can see on the top. There is explanation given. You can go through that also. So after that, all theoretical question, I guess. Which law states that internal energy of a gas is a function of temperature? Internal energy is a function of temperature. What is the answer? Joule's law, isn't it? Joule's law. Open system is one in which, can you unmute your mic? Can you share your answer and all? So now my theoretical topic is over. Gone.
The answer is C. Both energy and mass cross the boundaries of the system.
Yeah,
Energy and
answer is C.
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 Answer is C. Ratio of two specific heat of air.
1, 2,
1 or 1.4.
sorry.
So 1.4.
1.4.
Now this is a very quite often repeatable question, a very simple one. If you are getting a thermodynamics this kind of question, then you are very lucky. According to Avogadro's hypothesis,
I think A.
Can you close your microphone, please? Because
I think it's Gopal. I think I don't know why Gopal mic has some noise. Now I make it you mute. So you try with your. Are you using any microphone, Gopal? There is some noise we are hearing. Earphone. You check your earphone. So some noise we are hearing. Okay. How about question number 10? Question number 10. The answer is
A.
A, right? It should be A.
Yeah.
Yes.
Occupy all same. Isolated system.
No movement of mass. A.
A, neither mass nor energy crosses the boundary of
B. I think B.
B, because A, energy can transfer, right? So B, energy also, mass also cannot transfer. Should be B. So read the option, because when you're talking about thermodynamics, they have more theoretical statement. Ice and water form a very simple
heterogeneous system.
heterogeneous system.
Thermodynamics.
Which of the following is the property of system? Is somebody say thermodynamic for the previous question? It's a D, heterogeneous system, because it's a ice and water, no? It's a heterogeneous. Question number 30.
But hello, but
Yeah.
but ma'am, both ice and water get mixed, right? They are homogeneous.
No, cannot be. Ice and water
Two
cannot be
physical
mixed. Once the ice is
states.
melted, it's a heterogeneous stage. When ice started to melt, then only it become homogeneous. If you see water and ice, it will be two separate phase. It's a solid or semi-solid we can talk about, or the another one is a pure liquid. So it has to be heterogeneous.
But they are telling mixture of ice and water.
Uh,
The question is mixture of ice and water. When you mix it, they will both get mixed, right? The ice
it
will
will
start
mix,
melting in
it
water.
will be mixed. It will be mixed, but two phases you can see in that mixture. Not necessarily one mixture means it always has to be homogeneous. Not necessarily. Ice and
Okay.
salt, it's a homogeneous. Once it is mixed, you can see no more. Ice is being dissolved in the water. You cannot see solid phase separately and the liquid phase separately. But ice and water, you can see. Ice started to melt, yeah, then it become a no more ice there. That means it's all ice or melted. That means no more ice. Then it become a homogeneous, we can say. But if you see ice and water, that means it's a two different phase in that mixture. Then it is a heterogeneous.
Okay.
Question number 30.
System. Internal energy.
It's the property of a system. Why pressure and
All of the
temperature is not
above.
property? All of the above. Could be.
All of the
All of
above.
the above. Huh? Yeah. See, I would say one simple clue, whenever you see all of the above, that should be the right answer. Huh? 80-90%, there will be all of the above. If you see, that could be the right answer. Specific heat of air increases with increase in
C, I think.
Both pressure and temperature.
both pressure and temperature. We talk about here only temperature. Increase in temperature, specific heat increase, because specific heat we have at constant pressure and constant temperature, right? So constant volume.
Volume.
So,
Yes,
so
yes.
there, yes. So that means if you want to increase the specific heat, there will be possible a constant pressure, but temperature increase, always the specific heat will increase, whether it is a constant volume or constant temperature. Which are the following are thermodynamically reversible? Is there any more?
C, I
option?
think.
What's that?
Maybe C.
Throttling?
C. Throttling, is it a reversible?
You can unthrottle it, na?
How to unthrottle?
Like in the graph, you have shown one valve, so you can throttle